Hi, we're going to take a look at capacitors. We've done a lot of work with electricity so far, talking about very, I would say, abstract things about electricity. And now we get to look at something practical, something that actually shows up in an electric circuit. The first one that we get to learn about in this class is called a capacitor. And a capacitor basically consists of two parallel plates of conducting material separated by a gap. Now, if I were to take and hook a battery, the reason I write a V on the battery is because a battery supplies a voltage potential. And if I were to hook it up to one side of the plate and one to the other side of the plate, and this being maybe the positive and the negative terminal of the battery, charge will go up onto the plates of the battery. Why would they do that? Well, remember, positives and negatives want to be near each other. So by occupying space on these plates, they get to be near each other. That's all they want. They want a friend and to be near each other so they can say hi. This does create an electric field between these two plates, and energy is stored in this electric field. And that's actually the purpose of a capacitor, is to store energy by storing charge. I'm going to also draw this for you as our first schematic diagram. Now, a capacitor is represented in a circuit diagram, that's what a schematic diagram is, as two parallel lines. Kind of makes sense because that's kind of what it looks like. And a battery is represented by two parallel lines, but one is long and one is short. And the point behind the short and long line is that we've got a place of high potential and a place of low potential. Makes beautiful sense to me. And we'll put a V here and a C here. That leads us to an idea called capacitance. A capacitor physically consists of two parallel plates, and it has some physical properties. One of those physical properties is the total area of the plates. So we're seeing it from a side view, but these plates have an area. And also, there's the gap between them, which we're going to call little d. Capacitance is a measure of how much charge a capacitor can store per volt. And the reason it's per volt is because, I'm going to write this, capacitance is the amount of charge stored per volt. The reason it's per volt is because the stronger the battery is, in other words, the more volts it has, the more charge it can push out onto those plates. This is the first time I've referred to voltage as an electric push, but it won't be the last. That's how a lot of practical people, aka electricians and electric engineers, think of a voltage. They think of it as an electric push or an electric pressure. The voltage pushes charge out onto the plates. The more voltage you have, the more charge will go out there. But this capacitance is actually a physical characteristic of the capacitor itself. What it depends on are the area of the plate and D. So it turns out the more area I have of those plates, the more charge I can store. That makes so much sense because the area is where the charge sits, and the more area you have, the more room there is for charge. It's inversely related to the distance. The way I think of that is that if the distance is reduced, those charges are going to be nearer to one another. They will feel the attractive force between each other more if they're closer, which will entice more charges out onto the plates. The D, the smaller that is, the more charge will go out onto the plates for a given amount of voltage. Now there's a thing missing here, which is a constant, epsilon naught. This is the same epsilon naught that we learned about when we learned about Coulomb's law and the kind of alternate version of the K constant. So I told you it would come back again when we talked about capacitors, and here it is. Epsilon naught value, again, is 8.85 times 10 to the negative 12 Coulomb squared per Newton meter squared. If I have to find the capacitance of a capacitor, and I know what the area of its plates in meters squared and the distance in meters, I would just use this formula to find the capacitance. So let's do one of those real quick. This is a three-parter. A. Calculate the capacitance of a parallel plate capacitor whose plates are 20 centimeters by 3 centimeters and are separated by a 1 millimeter air gap. So we'll start with that. In order to calculate the capacitance, we have epsilon naught times the area over D. We have D directly, that's a 1 millimeter air gap. We don't have the area, but we have information that'll let us find the area. So let's do that. The area is going to be the height times the length, or the length times the width, or the width times the height, whatever you want to call those things. Those two dimensions multiply together, which is 20 times 10 to the negative 2 meters, multiplied by 3 times 10 to the negative 2 meters, which I get as 6 times 10 to the negative 3 meters. D is 1 times 10 to the negative 3 meters. Alright, so let's plug them in. We got C is epsilon naught 8.85 times 10 to the negative 12 unit stuff. I'm skipping it. Times 6 times 10 to the negative 3 meters divided by 1 times 10 to the negative 3 meters, and it all comes out to 5.3 times 10 to the negative 11. Well, I forgot to tell you what the units of capacitance are. Shame on me. It's a capital F, which stands for farad, named after the lovely Michael Faraday. Okay, sorry about that. I forgot to mention this. We actually do have a unit for capacitance, and it is the farad. Better late than never. Alright. B, what is the charge on each plate if a 12-volt battery is connected across the two plates? We use that word across a lot. When we apply a voltage and we use the word across, it's because we're setting up a difference in voltage from one side to the other. Okay, so we think of voltage as being across things because they're voltage differences. We learned that capacitance is the charge per volt. So that means that the charge is going to be the capacitance times the voltage. And so we can take that capacitance of 5.3 times 10 to the negative 11 farads and multiply it by the volts, 12 volts, and we will get 6.4 times 10 to the negative 10 coulombs of charge. Now it says across each plate. Well, that's how much charge you're going to get. On one plate it'll be that much charge positive, and on the other plate it will be that much charge negative. Alright, finally, C, what is the electric field between the plates? Now we're going to have to roll back a little bit. Remember, we learned a formula that told us a relationship between voltage and electric field and distance when you had a uniform electric field. Well, guess what capacitors make? A uniform electric field. And so this formula will get used quite often in capacitor problems because it applies to capacitor problems. So if we solve this for the electric field strength, it's the voltage over the distance, and that voltage was 12 volts, and the distance, if you recall, was 1 times 10 to the negative 3 meters, and that comes out to 1.2 times 10 to the 4 volts per meter. When I connect a battery to a capacitor, I literally am removing charge from one of the plates and putting it on the other. Okay, I'm taking electrons away from what becomes the positive plate and depositing it on what becomes the negative plate. That's the function of the battery. There is some work involved in doing that, and if you do work, you're giving something potential energy in this case. The amount of work I do is varied. Removing the very first electron from here and putting it over here doesn't take much work. But as I remove more and more charges, remember, putting a bunch of negatives in one spot, they're going to resist having more electrons put in there because of the repulsion. So the amount of work you have to do to get each additional charge becomes more and more and more because they're more force resisting it. The net effect is that it's just like compressing a spring, honestly. And so the energy storage, due to all that work done, has a similar look to it. It's 1/2 the total charge times the voltage. Again, we're not going to do the calculus, but you get the picture. Now, we know that Q equals CV. If I substitute that in here, I get that this is also equal to C times the voltage squared. And I can solve this for V and substitute it in here, and I get that it is equal to 1/2 Q squared over C. So you notice we can represent this using any two of the three variables that show up in this equation. And using this is simply a straight matter of plugging numbers into the equation. Let's do a very quick calculation example. So I have a camera flash that stores energy in a capacitor whose capacitance is 150 microfarads, and that is stored at 200 volts. How much electric energy can be stored? We want to know what is the potential energy of this situation. I have two things. I have the capacitance and the voltage, so let's use the expression at the top that has capacitance and voltage in it. This one. So I'm going to put that in here. 1/2 the capacitance times the voltage squared, and substituting, I get the capacitance is 150 times 10 to the -6 coulombs, and you have 200 volts squared. What does it come out to? 3 joules. Don't you like it? It is really that simple, and that's all you're ever going to need to do with that formula.